we are going through the topic of traffic control devices. We are discussing traffic signals. What we have discussed up to now is types of signal operations, signal coordination, type of intervals. Okay, and then we looked at the calculation of cycle time and what else? Yeah, cycle length, and we finished with the topic of critical link, which is the link from which you take the volume for your analysis. And the last thing in that one was you can have multiple critical links at the same time. You can have multiple movements in the same phase. We call them overlapping phases. Okay. Moving on. Now we will discuss the measures of effectiveness for an intersection. Measures through which you know the performance of the intersection. Okay. How do we measure the performance of a highway?
Speed and travel time.
Speed and travel time. Okay. Anything else? Anything which can come in the exam?
Level of service.
Level of service. And to calculate level of service, I need what? And density. Okay. So you mention all these things: speed, level of service, travel time, flow rate, density. Okay. These things work on highways because on highways we have speed and all these things. But on intersections, these measures cannot work because on intersection you have a control device, stop sign, roundabout. Okay. And it's an intersection. People are supposed to come and stop. Okay. Either you force them to stop or they have to stop for safety, right? So when they stop, their speed is 0. Their flow rate is 0. Their density is
Non-zero.
huh?
Non-zero.
Non-zero, yeah. Okay. So it's maximum. Density becomes maximum. But all of these things are forced. Get my point? They are not because I have very high flow or too many cars. These things become 0 or maximum because of the force control device. Okay. So they will not work. For intersections, we use 3 different measures of effectiveness to measure the performance, which are delay, queue, and stops. Okay. Delay meaning if the delay is higher, that means the performance is low. Queue length. How many people are in the queue? What is the length of the queue? How many people in the queue? Okay. Longer the queue length, performance is low. Number of stops. How many vehicles have to stop at the intersection? From the total, how many have to stop at the intersection? More vehicles have to stop, the performance is clear? Okay. The most common, the most important one is delay. Okay. The most common and the most important measure of effectiveness is delay. Delay is of 4 types. We have already discussed 3 of them. Okay. The first one is stop time delay, which is very easy. The time when the car is stop. Okay, we will use waiting for one thing. Stop. Okay, stop time delay means the car is okay. Whatever makes you happy. Then we have approach delay. We gave it another name which is control delay. You are mentioning it, right? You mentioned it, right? Then what is control delay? So you come to the intersection, you have to decelerate. Okay, and you may have to stop. And once you cross the intersection, you will accelerate. Okay, all this is part of approach delay. Another name for approach delay is control delay. Okay, we covered it in the travel time topic. So approach delay and control delay are same. Okay. Then we have timing queue delay, which is again very easy to understand. Time when the car is where? Yes. Where? time in queue delay. Where is the line? In the queue. Okay, then we have travel time delay. Travel time delay means the difference between the actual travel time and the desired travel time. Actual and desired. Their difference is called as travel time delay. Actual travel time means observed. Okay, you go and observe. Okay. Desired means as per your choice, right? Okay. We don't have any study for travel time choice, but we have a study in which we find out the choice of drivers about speed. Which speed is that? Free flow speed. No. Okay, free flow speed. So desired travel time comes from free flow speed. Got it? Clear? Don't know what is it, but clear, huh? Totally clear. Okay, so travel time delay is the difference between actual and desired. Actual can be observed, desired comes from or calculated from free flow speed. Clear? Now clear now? In this figure you can see 3 out of the 4 delays. Okay, the types I mentioned here. On the x-axis I have time. On the y-axis I have distance. Distance upon time is speed. So you can see 2 lines here, right? One is the desired line. The top one is the desired line. Okay, and which speed gives us a desired line? Free flow speed. So this, the first line is according to the slope of free flow speed. Clear? The next one is the actual one. So you can see it's going here and there. Okay. So it was at a particular speed. Then you can see at this point it is doing what? What is happening here? Huh? This is stop. Before stop? Huh? I cannot say no. Huh? Deceleration. Yes, deceleration. Okay, and then this is the stop time delay. So you cannot, you can see the line is going nowhere now. Okay, here it was, the slope changed, but it was still going a little bit up. Here, nothing. So this is what we call as stop delay. Okay, and what is happening here? Acceleration, and then you can see the line goes back to normal again. Okay. So if we just look at this part where the line is flat, this is stop delay. If you include the deceleration and the acceleration part as well, we call it approach delay. And if you can take the difference between the desired and the actual, we call it travel time delay. Okay? The last one was which one? Which is missing here? Which type of delay is missing? Time in queue is missing because there is no queue here. I cannot show the queue here over here. It's a 2D figure, the queue cannot be shown. Clear? Okay. For that I have another one. So again we have time on the x-axis, and for our convenience they have marked the signal indication or intervals on the time axis. Okay, so I know where is green and where is red. On the y-axis I have total number of vehicles. Total. Okay, cumulative. Clear? So when the time is green, I have the vehicles which are approaching the intersection and they are moving. Okay, no problem here. Then the time becomes red, and then you see now it is dividing into 2 lines. Okay, one is still going up, the other one goes flat. The one which is still going up, this is the arrival line. This is showing the number of vehicles arrived. Okay, so even if the signal becomes red, the arrival will not stop. People will keep on coming. Okay, but the departure or leaving the intersection is stopped. So during the red phase, you see the departure line is flat. Okay, then the time becomes green again. So arrival is still going up, but now the departure has also started. Clear? Okay. Now, this is the difference between arrival and departure. See? So, what do we call the difference between arrival and departure? Vehicle in the queue. That's why they wrote queue, right? Okay. You don't know I'm joking or serious, right? Serious. This is number of vehicles in the queue. Huh? Number of vehicles in the queue. Arrived more, departed less. Who is remaining in the queue? Clear? Okay. So if you take the difference, at any point it will give you number of vehicles in the queue. Okay. And then what is W? What is W? Stop vehicles. They are making it easy, right? The Q was for Q, right? So W is for W. Yeah, waiting. Yes, waiting time. Yes. Okay. So this vehicle arrives at this time and leaves at this time. So you take the difference. That is the waiting time. Okay, waiting time, which is the time in queue delay. The vehicle came, it joined the queue, right? And then it left. So waiting time is the time in queue delay, the fourth one. Got it? So if you take the difference on the y-axis, you get how many vehicles are in the queue. If you take the difference on the x-axis, you know how much time the vehicle was in the queue. Clear? Clear? Okay. Yeah. So I said vehicles on the y-axis, time on the x-axis, right? Vehicles upon time, flow rate. Okay. So this line has a slope, okay, which is the flow rate of this line. This line is showing what? Vehicles? Huh? Yeah, but which vehicles? Arrival. Okay, so this flow rate is the arrival flow rate. The slope of this line is the arrival flow rate, which is V. V is arrival flow rate. Got it? And then you have the slope of this line, which is also a flow rate, right? Slope is the flow rate, right? Because upon time is the flow rate. The slope of this line is called S. Okay, S is what? Saturation flow rate. Okay, you can call it departure, but the term S means saturation flow rate. Okay, so we have an arrival line. The slope of that line is the flow rate of the vehicles arriving. We have a departing line, and the flow rate of that is called the saturation flow rate. Got it? Clear? Okay. Now we have a guy called Webster, and he came up with some equations related to signals. The equation for cycle length, which we used, and he also gave us the equation for uniform delay of the signal, delay at the signal. He is calling it uniform delay because this is the condition in which every vehicle added to the flow increases the delay by a fixed amount. Okay. Uniform delay happens. First of all, uniform delay happens when capacity is more, demand is less. Uniform delay happens when capacity is more, demand is less. Okay. Why we call it uniform? Because every vehicle in this condition is increasing the flow, the delay by a fixed amount. For example, if we have 5 vehicles and the delay is 10 seconds. 5, 10. Every vehicle is adding by how much?
2 seconds.
2 seconds, right? If I make it 20 vehicles, then delay is 40. If I make it 40 vehicles, then delay is 80. Got it? This is called as uniform delay. But it only happens when demand is less, capacity is more. So in that condition, you want to calculate the delay of the signal. This is the equation. Half R into B. What is R? Red time. What is R? Red time. What is B? Number of vehicles in the queue. Okay. R is red time. B is number of vehicles in the queue. Okay. Now you see this equation is very nice, very simple, very small, very cute. We don't know this. So we'll mess it up. Okay? We'll start messing it up one by one. I cannot do anything with half. You see now, even for half I can write 0.5, right? But I will not. Okay? I don't like simple things. Okay? So we'll start with R. What was R? Red time, right? We have a small g which is called as effective green. Effective green. Okay, the time in which the vehicles are moving at saturation head. G upon C. C is the cycle length. So G upon C means the portion of cycle length which is effective green. Okay, G is effective green and C is the total cycle length. So G by C means portion of cycle length which is effective green. And 1 minus this is the remaining, right? This is the portion with the effective green, and 1 minus this will be the remaining portion. Remaining portion is called as red. Clear? The portion of cycle length which is not effective green. Clear? Okay? So this one done. Now I need what other parameter? V, right? V is number of vehicles in the queue. Q starts when? Here, right? Q starts at the start of red. Where is the end of Q? Where is the end of Q? Where the two lines are intersecting again, right? Okay. So arrival meets departure. So there is no Q now. Because we said the difference of arrival and departure is the Q, right? So where the two lines meet, Q is gone. Okay. From here to here, what do I have on the time axis? Look at the time axis. From here to here, I have red. Then after red, the Q will not vanish immediately. It will take some time. Okay. So that time is called as clearance time, TC. So after a signal will become green, the Q will start to move, but it will take time TC to go completely. Okay, TC means clearance time. Okay, so anybody who arrived during red is in the queue. Anybody who arrived during time TC is also in the queue. Clear? Okay. I want to calculate how many vehicles are in the queue. I know the time now, which is red and TC. I want to know how many vehicles are in the queue. Okay. I have two lines, right? I have two lines here. Okay. Arrival and departure. I can use any one of them. If I use arrival, so the slope of this line is V, multiply by what time? R plus TC. This will give me number of vehicles in the queue. Okay. Arrival rate multiply by the red time and the clearance time. This will give me number of vehicles in the queue. I can use the other line as well, the departure line. Okay. What is the slope of departure line in red? 0, right? So I cannot do anything in red with the departure line. The departure line only has a slope in time TC. Okay. So the slope of the departure line is S multiplied by TC. Clear? So if you want to use arrival, then arrival flow rate multiplied by R plus TC. If you want to do departure, then S multiplied by only TC. Clear? Okay. So this is, but they are the same vehicles, right? Vehicles in the queue. So the answer should be same. So this is what we have done here. This is from the arrival line and this is from the departure line. Okay. From this equation, I will get the value of TC. Okay. I'll get the value of what? TC. Okay. Now, what do I actually want? I want to find out V, how many vehicles are in the queue, right? Which can be equal to this thing, right? This is the number of vehicles in the queue, right? Now here I have found the equation of Tc. So what I will do, V equals to V into R plus Tc. So Tc, I have an equation for Tc, I will put that equation, so V equals to this. Got it? Okay or not? Yes, last row. Huh? What is this? Huh? You are saying what? Yes or no? Okay. In Pakistan, they say yes like this when you are getting married. Okay. You're not married, right? Keep practicing. Okay. So now, I am trying to calculate uniform delay. Uniform delay equals to half R into V. This equation was very simple. I don't want simple. I want to mess it up. So first of all, I found this thing for R. Then I found this thing for V. So instead of doing half R into V, I will do this into, okay, V into the equation of V into equation of R. Okay, clear or not? Okay, so this is the final equation. Now you can see here they are using the small a here. Small a stands for aggregate. Small a stands for aggregate, total. So this equation gives you total delay, total. Okay, and if I want average, then if I have total and I want to calculate average, then what do? Divide by the number, right? So I will divide this equation by number of vehicles. Okay, so this one was for total. I divide by V and I get the equation for average. Okay, so this is for average delay and this is for total delay. Clear? Okay? In the queue. Okay, but this is average. Okay, I know what you're trying to say. I still thought the same thing. Okay, but this is what they are giving. Okay, so the above equation is for total delay and this one is for average delay. Okay, clear? Okay, now in this equation you can see we have V upon S. Okay, V is what? Arrival flow rate and S is departure and the other name for it is saturation. Okay, now we did the first example which we did in this topic. We calculated the capacity using saturation flow rate, which is what you see on the top. A small c is the capacity equals saturation flow rate multiplied by G by C ratio. Okay, what is G? Effective green, and C? C is capacity, right? Cycle length, very good. C is cycle length, okay? C is cycle length. This is small c capacity, capital C is cycle length. Okay. What does this equation mean? Saturation flow rate is the maximum flow rate in 1 hour for a signal without interruption. Saturation flow rate is the maximum flow rate in 1 hour from a signal without interruption. Okay. So capacity equals to saturation flow rate if there is no interruption. Okay. If the whole cycle is what? Green. Green means no interruption, right? Okay, so if G by C ratio is 1, then capacity equals to saturation flow rate. Okay, but actually G by C ratio is not 1. Okay, so capacity equals to S multiplied by G by C. Clear? Okay. Yes. Clear? Okay. So if capacity equals saturation flow rate multiplied by G by C, then saturation flow rate equals capacity upon G by C. Okay. Clear? Now I had a equation, this equation, right? In this equation I have saturation flow rate. Saturation flow rate equals this. Okay. So in the average delay equation, I'll remove saturation flow rate with this thing. Okay. When I do this, it was V upon S removed. Now I have V by C into G by C. Now remember, this is G upon capital C, green upon cycle length. This is V upon small c, where V is the arrival and C is the capacity. Got it? Okay. Capital C is cycle length, small c is capacity. Okay. Clear? Now V by C ratio can also be represented with X. X means V by C ratio. X is V upon C ratio. Okay. Clear? Okay. Now this V by C ratio is very important. We use V by C ratio in the equation of calculation of roundabout delay. We use V by C ratio, or we can use V by C ratio to calculate the level of service as well. In the level of service topic, there was a table. Instead of using density, you can use V by C ratio. Okay. So this is a very important ratio. You will see them in many equations. Okay. We have the situation, intersection approach has an approach flow rate of 1000 vehicles per hour. Which flow rate is this? Look at the equation. Tell me which value is this. Which value from the equation is given here? 1000 is which value? V. Okay. Approach means arrival. Okay. So V is given. Then we have saturation flow rate, cycle length, G by C ratio. Okay. They want to find out the average delay. This is the equation of average delay. Okay. Now tell me which value is missing. Which value is missing from the equation? Capacity is missing? Yes, capacity is missing. Yes. Capacity is missing, right? I want to calculate X or V by C ratio. I have V, but I don't have capacity. Clear? Okay. How will I calculate capacity? I have the equation over here. Capacity equals what? Saturation flow rate into G by C ratio. Are these things given? Yes, they are given. Okay, so capacity, I'll go there. So capacity is saturation flow rate multiplied by G by C ratio. How much? Sorry. One 1540. This was the only thing missing. Now you can calculate the delay. Give me the delay. Huh? 2.36. Anybody else? I got different answers in that. $14.2. Okay. This is the value I got from the other section, so this should be correct. So I wrote seconds per vehicle. Every vehicle is adding how much delay? 14.2 seconds. And why I am saying every vehicle is adding the same amount of delay? Because I am calling it uniform delay. This is what uniform delay means. You add one vehicle, delay increases by this much. Okay? Clear? And when do we have this condition? What is the condition to have uniform delay? Demand is less than capacity. Yes, you had a question.
For the current situation, we didn't increase any payments. The current delay is 14.2 seconds.
Clear or not? Okay? Any questions? Okay. Okay. Moving on with the topic of signal design. So we now know how to calculate cycle length for the signal, and we know how to calculate the delay of the signal. Okay. But let us look at the process of signal design. This process follows 3 steps. Okay. There are 3 steps to design a signal. The first step is to develop a phasing plan. Develop a safe and effective phase plan. What does a phase mean? What do you mean by a phase? Number of
Movement in one time.
number of movements at the intersection. What is a phase? What is one phase? Number of movements. One movement is one phase. But what does it mean? What about this movement? Which thing of the movement is called a phase?
Allowed movements.
Allowed movements.
At one time.
Yes. Anybody else? What is a phase? What is included in the phase? Phase the time. Phase the time. Okay, a part of the cycle length. This part. It includes what? Green, all red, yellow. Okay. So phase includes green, all red, and yellow. Every movement has one phase. Every movement has one phase. Okay, and that is the phase in which that movement will have green, yellow, and all red. Okay. So the first step of design is to develop a phase plan which is safe and effective. Okay. Like effective meaning that it should be suitable for the movements you have, and it should be safe. Okay, so you can allow different movements in one phase, it is good, but these movements should not be conflicting. So last time I gave the example, you can allow one going towards east and the one going towards west. You can combine them, no problem. This is effective. Okay, or you can combine one going straight and one going left. You can combine them. This is effective. Okay, and it is safe as well. Both these options are safe. Okay, or you can combine left turning from one side and straight from the other side. It is very effective in killing people, but it's not safe. Okay, so this is what they are saying. Phasing plan means decide which movements can go in a phase. Decide the combination of movements which you can assign to a phase. Okay, and this depends upon the intersection design. We will discuss it later on. So this is the first step. Okay, but the main idea here is do not combine the movements which are conflicting. That will be unsafe. Okay. Second step is designing the timing of the signal. The first timing we design is yellow and all red. Okay. Yellow is also called as change interval, and all red is also called as clearance interval. Okay?
Which yellow?
After the green
Before
or
the red?
After the after the
So before the red?
before the green once.
It is not in the phase end.
Huh? It is. It is. Not here. They don't have. They are poor people. Don't have. They are rich people. Okay. Even our lanes are more wider than that. Our roads are more wider than that. Okay. If you go to any Western country, you will not find even the road which we have inside the campus. This can be their main road. Okay. Thank you. So we will start with yellow and all red time. Why? Because these two timings depend upon the design of the intersection. They don't need demand, volume, and other things. If you know the design of the intersection, you can calculate these two things, yellow and all red. Okay? And obviously you are trying to install a signal, that means you already know the intersection. There is already an intersection, right? That's why we are designing the signal. Okay? So design of the intersection is required for these two things. Then since you already developed the phasing plan, now you know in each phase which lanes are open. From these lanes, you will pick one for each phase as a critical lane. Okay, and you will take the volume of that lane. Okay, that will be your critical volume. For the signal design, you will add all the critical lanes. Okay, so you have three phases. Each phase will have its own critical lane. You will have three critical volumes, one for each phase or for each lane. Okay, and the final value is the summation of all these three. Got it? Clear? Okay. Next thing to be calculated is lost time in one phase, lost time for the entire cycle. And we have discussed it earlier. Okay. Lost time of one phase, lost time of the entire cycle. Then next step, calculate the cycle length. We have seen the equation of calculating cycle length yesterday with the examples. Okay. So the next step is calculate cycle length. Then we said a phase is which timing? Yellow, orange, and green, right? We already calculated two of them, right? Which two are calculated? Yellow and orange already calculated. So we are just left with what? Green. Okay. So the last step is calculate green for every phase. Which green? Effective green. Our design is related to effective green. Okay. Our design is related to effective green. Once you calculate effective green, the design is done. The design is done. The actual green time, you already have an equation. We have seen it earlier. But if you know these things, you can calculate the actual green. But this is just to show the graphs. Okay? It's like design calculation with the construction drawing. So the actual green is like construction drawing, just for the contractor, for the user. Okay? As an engineer, what is more important for me? Effective work. Okay? Clear? So once you are at this step, signal design is done. Okay? The third step is for pedestrians. And it is only done when pedestrians are available and they are allowed to cross the intersection. Okay? And obviously, if pedestrians are available, then signal becomes very easy and safe for them to cross, right? So normally we allow the pedestrians to cross at the signals. Okay? But they should be there. Okay? So if there are pedestrians available, then you should know how much time they need to cross the road. First of all, calculate required time by the pedestrians. Then cross-check with the signal timing. The pedestrian time, is it equal or less than the time you are already providing for the vehicles? If it is, pedestrian will cross with the vehicle, no problem. Okay, signal will become green for the pedestrian. Signal will become green for the vehicles, pedestrian will move with them, and it is enough time for him or her to cross. Okay, so if it is enough, you stop. If it is not enough, you have to increase the time according to pedestrian requirement. The pedestrian needs 10 seconds. Are you giving at least 10 seconds for the vehicle green? If it is, fine. If not, and it is less, increase the vehicle. Okay? And pedestrians normally cross parallel. Okay? So if the vehicles are going towards east, they have the green towards east, the pedestrian will go parallel to them. Okay? Clear? When this signal will become green, I am waiting here, I want to cross like this. When this signal will become green, and these vehicles will go, I will run with them. Okay? I'll try to run faster than them. Clear or not? Okay, the first step is to develop the phasing plan, and this is what we will discuss right now only. So, if you pass through different signals, okay, phasing plan is the combination of movements you are allowing in one phase, right? If you pass through multiple signals, now when you go home, instead of looking at your phone, if you look at the signals, you will see at each signal there is a different combination. They are using different combinations. Okay, so maybe if you pass through 3 signals, you will see 3 different phasing plans. Okay, so there is no fixed phasing plan that you have to do this, this, this. It depends upon you. They are only guidelines. If you follow the guidelines, then whatever plan you have is good. Got it? So there is no value or there is no fixed phasing plan. Clear? So I'll just give you the guidelines. The first guideline already mentioned that the phasing plan should be safe. Okay, conflicting movements cannot happen in the same phase. Clear? Other thing, which is the opposite of this, without the conflicting movements, try to combine as many movements as possible in one phase, because it will reduce the number of phases. When you reduce the number of phases, you have less lost time and more capacity. Okay, I showed you in the last lecture. Okay, capacity increases when you have less phases. To have less phases, I should combine the movements, but it doesn't mean I combine everything. I have to look at safety as well. Clear? Okay, try to combine but non-conflicting movements. Okay, other thing, look at the local standards. Consider the local standards. Okay, so here we have, right turning, right? So right turning is allowed. You come to the signal, you have the chance, you will take the right turn. Okay, in Pakistan we have the left turn, because we have the left hand drive. Okay, so these are the local standards. So the phasing plan which is working here will not work in Pakistan. Okay, even there are differences between here and Saudi as well, neighboring countries, but there are differences in the design and in the rules and regulations. Okay, so the same phasing plan may not work in both countries. Clear? So look at what are the local standards, what are the local norms and culture, so you don't create confusion for the drivers. Okay, and the third thing is design of the intersection is according to your phasing plan. Design of the intersection is according to your phasing plan. For example, very quick and clear example, if you are giving a separate phase for left turning, so left turning has a separate phase. Okay, it has its own green and yellow. Okay, that means left turning should have a separate lane as well. Okay, you cannot have a separate phase without a separate lane. And if you are giving a separate lane, how the drivers will know? You have to put marking as well. You may have to put a signboard as well, big signboard. Okay, if it is more critical or high speed road, you may provide a traffic island as well. So all these things are happening because of what? Because of your phasing plan. You decided I want a separate phase for left turn. So now you have to do all these things. Clear? Okay, so design according to phasing plan. Once you have the phasing plan, you can show it in 2 ways. There are 2 diagrams to show the phasing plan. One is called as a phase diagram, the other one is called as a ring diagram. Okay, both of them have the same purpose, showing the movements of different phases. You can do it through a phase diagram or a ring diagram. What is a phase diagram? It shows all the movements in one phase in a box. Okay? All the movements in one phase in a box. Okay? In any direction, from any direction. This is called a phase diagram. In a ring diagram, each box shows the movement of one phase which are happening from one face. Okay? Each box in a ring diagram shows the movements of one phase happening from a face of the signal. What is a phase? A direction. A phase is a direction. Okay? So we have signal in each direction, right? A different pole in each direction at least. Okay? So a ring will show what is happening in each direction with one box. Okay? You may allow different directions at the same time, but then in the ring diagram you will see different boxes for the same phase. Okay? I will show you the examples, no problem. Okay? But a phase diagram, all movements, any direction, one box. Ring diagram, all movements in one box, but only for one phase, one direction. Clear? Before I show you the example, the legend or the notations we are using in the phase or the ring diagram. So you see the arrows are showing the directions. Straight arrow means straight, left means left, right means right, and so on. You see some of the arrows have dotted lines. Dotted means the movement is allowed. The movement is allowed, like the right turn. Okay, so you don't wait for the signal, you take the right turn. If it is dotted, dotted means that movement is allowed. It's not by the signal. Clear? And then you see, so you see this one and this one and this one. Okay, straight, right and left. Straight, right and left. Okay, what is the difference? Here all three from one line, right? And here from two lines. So lines are representing the number of lanes. Lines represent number of lanes. So how many lanes I have here? One. How many lanes I have here? Two. Okay, if you have more lanes, you will keep on increasing the number of arrows. Okay, clear? Okay. So the first one is a phase diagram, the second one is a ring diagram. Okay, so you see the first one. One box is showing movement from opposite direction, right? So in a phase diagram, it can happen. Okay, look at the ring diagram now. One box, one movement on one side, other movement on the other side. They are in the same phase, same phases. The ring and the phase diagram are showing the same phases, the same design of the signal. Okay, but in the ring diagram, they are in different boxes. Now, how do I know it's the same phase? Because the boxes are parallel. Okay, so I am showing different movements parallel to each other in a ring diagram. That means it's the same phase. Clear? Okay, but you will not put them in the same box. Clear? Okay. Now you see here in this phase and ring diagram, I have a separate phase for left turning, right? I have a separate phase for left turning. Look at the intersection. I added something. What? Yeah, the channel or the lane for left turn. Because I have a separate phase for left turning, I have to add a lane for left turn. Clear? Okay, this is what I was talking about. This one. You should look at the third phase. They don't have the ring diagram. Look at the third phase. Does it have any movement? The third phase. Phase C. Does it have any movement? No. So this is an exclusive pedestrian phase. It's only for pedestrians. Everybody has right now. Only pedestrians can do. Okay. I saw this in Belgium. They have this push button. Okay. So you come and you push, and then all directions become red. Okay. So you can cross in any direction. Clear? Okay. So, but this one is a phase diagram. Okay, any questions? Okay, thank you.